Welcome to The Explainer. Today, we're stepping into the high-stakes, absolutely mind-bending reality of building mega highways beneath millions of gallons of crushing, pitch-black water. We're going to look at the science of engineering the abyss, basically taking the most massive transportation bottlenecks on the planet and solving them by going directly underneath the ocean floor.
Okay, to really wrap our heads around the scale of what we're talking about, just look at this number, 390 meters. That is the terrifying, record-breaking depth of Norway's upcoming Rogfast Tunnel. To put that into perspective for a second, you could literally take the entire Empire State Building, drop it into the water, and it would easily fit entirely between the tunnel floor and the surface of the fjord right above it. It's just a staggering depth that pushes human engineering to its absolute breaking point.
Now, you might be wondering, why even go to these dangerous extremes? Well, it's because of geography, exactly like this. Norway's coastline is, quote, a jagged mosaic of mountains, islands, and open water. These stunning fjords were carved by massive glaciers, and today they present a complete geographic nightmare. For drivers on the vital E39 highway, this landscape forces a grueling 21-hour journey that involves navigating 9 separate, slow-moving ferry crossings. It's actually the most ferry-dependent road in all of Europe. Fun fact, back in 1647, the earliest postmaster would row across these open fjords just to face vertical climbs of 1,500 meters on the far shore.
All right, let's dive into this. Our explainer today breaks down into 4 clear parts. 1. The ultimate engineering challenge. 2. 3 ways to build. 3. The battle against water. And 4. Pushing the limits.
So, starting right off with part 1, the ultimate engineering challenge.
Before we get into exactly how we build these marvels, we really need to understand the incredible economic and logistical pressures that force us into the deep in the first place. To understand why we build these, just look at the Botnafjord bottleneck. This massive fjord stretches 45 kilometers inland. It's a staggering 20 kilometers wide at its mouth, and it has an incredibly deep and steep topography. But it is absolutely vital. The region separated by this water produces over 20% of Norway's entire GDP through fishing, oil, and natural gas. And right now, a rapidly growing volume of heavy truck traffic relies completely on single-lane roads and slow ferry crossings. The economic pressure to solve this bottleneck is just immense, mostly because modern commerce simply cannot wait for a boat.
Now, you're probably thinking, why not just build a massive bridge, right? Well, while deep water tunnels are highly complex and definitely costly, they have some massive advantages over bridges. They perfectly preserve natural sightlines, they're completely immune to the brutal freezing coastal weather and wind, and, crucially for a place like Norway, they leave vital shipping lanes completely unobstructed for marine traffic. Which brings us to part 2, 3 ways to build. Let's see how we actually conquer the seabed. To actually conquer the seabed and make these submerged highways a reality, engineers generally choose from 3 primary methods. And it all depends on the soil conditions, the depth of the water, and the surrounding urban environment. First up, we have cut and cover. This is where you dredge a shallow trench right in a riverbed, build the tunnel inside it, and just cover it back up. Second, bored tunnels. This involves using a massive tunnel boring machine, or TBM, to literally chew through solid rock deep underground, installing segments as it goes. And third, the immersed tube method, where you prefabricate the tunnel segments, float them out, and sink them down.
The immersed tube method really stands out because it is just an absolute logistical marvel. Engineers construct these massive concrete or steel segments entirely on land, often in dry docks. Then they seal the ends with bulkheads to make them buoyant, float them right out onto the open water, align them with pinpoint millimeter accuracy, and submerge them into a specially prepared trench on the seabed. Once they're down there, they get linked together, the water is pumped out of the joints, and they are sealed tight underwater. It is quite literally like assembling giant Lego bricks in the pitch black under crushing water pressure.
Moving on to part 3, the battle against water. It's time to defeat the pressure.
Okay, we're going to zoom way in now, shifting our perspective from massive, multi-ton concrete tubes to the microscopic level. Notice the red arrows here. We have seepage path 1, which is the gasket-to-gasket line between the rubber seals, and seepage path 2, the gasket-to-concrete segment line. These are literally the weak points of the entire multi-billion-dollar tunnel. If external water pressure exceeds the peak contact stress of the rubber along these specific paths, tiny gaps form and the whole tunnel floods. Engineers actually use AI-assisted analysis to predict these exact microscopic routes, what they call the control path, where crushing water pressure might overpower the gasket.
To prevent a catastrophic breach, the physical geometric design of the rubber matters immensely. Here, we're comparing the internal hole geometries of 2 different gaskets. Section D, over on the right, has what's called a high opening rate, meaning larger closed hole areas inside the rubber itself. The AI models show that because of those larger holes, it fails to fully compress under extreme pressure. But Section A, on the left, has an optimal geometry. When it's squeezed, it maintains its perfect shape and creates a flawless, impenetrable seal.
And obviously, engineers aren't just guessing which shape will work best. The stakes are way too high for that. Instead, they use highly advanced finite element analysis, or FEA. They mathematically modeled this specific rubber as a hyperelastic material using something called the Mooney-Rivlin model. They calculate complex parameters for a very specific material hardness, shore hardness 70 to be exact. Using AI, they digitally crush these virtual gaskets in simulations from 0 to 8 millimeters, perfectly predicting the stress distribution before a single drop of ocean water ever touches the real thing.
And honestly, the results of those intensive AI stress simulations speak for themselves. Comparing Section A against the other designs, Section A is the clear definitive winner. Why? Because it provides the most stable, continuous peak contact stress growth at that highly critical gasket-to-gasket interface. The data proves mathematically that it can hold back the crushing forces of the ocean far better than the alternatives, which gives engineers the ultimate confidence to just go ahead and build. Let's wrap things up with Part 4, Pushing the Limits, because now we're talking about record-breaking projects.
You see, mastering that microscopic material science is exactly what allows us to scale up to unimaginable megaprojects. You simply can't build big without mastering the microscopic. We can trace the epic, historical evolution of the immersed tube over more than a century of innovation. It actually started incredibly modestly back in 1893 with a tiny 6-foot sewer main in Boston called the Shirley Gut Siphon. By 1910, we had scaled up to the Michigan Central Railway Tunnel, and in 1928, the Posey Tube in California, which was the very first for road traffic. Then things just got huge. We hit 55 meters deep with the Marmaray Tunnel in Turkey connecting Europe and Asia in 2013, and the staggering 6.7-kilometer immersed portion of the Hong Kong-Zhuhai-Macau Bridge in 2018.
Which brings us full circle, right back to Norway's Rogfast Tunnel. This is the ultimate megaproject actively rewriting the rulebook of subsea construction today. We're talking about an unbelievable 27-kilometer-long twin-bored tunnel that plunges those 390 meters deep. It even features a highly complex 200-meter-deep multi-level interchange situated directly beneath the island of Quitsoy, extending in 4 directions across 4 separate rock faces. It's actually being excavated from 3 sites simultaneously right now, and when it's done, it will finally eliminate those ferries and completely revolutionize the E39 highway.
From the microscopic science of predicting rubber gasket failure using AI to the jaw-dropping reality of a 27-kilometer-long megastructure plunged beneath a fjord, the progress is just breathtaking. It really leaves us with one provocative thought. As we continue to dig deeper and build longer, what impossible barrier is human engineering gonna cross next? Thank you so much for hanging out with me for this explainer. Keep wondering and keep learning.